refer to some of these very basic, simple problems on electromagnetic induction that involve deployment of the straightforward concepts that we've learned. No rocket science involved in these problems, but I'm assuming you would have attempted a few problems by this time, and that we should be ready to explore these problems together. Okay? So, the sheet titled Electromagnetic Induction the first problem is about a conducting ring of radius A. These are two mutually perpendicular diameters. This is a conducting ring of radius A. And it's fixed at the point P. Fixed at the point P. And in this region, there is a magnetic field B going into the plane of the board. Magnetic field B going into the plane of the board. Now, these are 2 points P and Q. And the ring fixed at P is rotated with an angular velocity omega about an axis passing through P and perpendicular to this plane. That's what it means. I hope all of you are able to visualize how it's rotated. Fixed at P, it's rotated with an angular velocity omega. This is the axis of rotation, right? Given this, we want to find the induced polarity between the points P and Q. So if you look at P and Q, the induced polarity between P and Q could be obtained by looking at a straight conductor joining P and Q. Recall that? So now we have a conductor, straight conductor PQ, hinged at P, given an angular velocity omega like this. And realize if A is the radius of this ring, PQ is of length A root 2. That's the length of PQ. And the induced EMF in PQ, epsilon cross PQ, is going to be half B omega into L squared. Right? Now, if you look at any element here, then that element will have a velocity v like this. V is like this. B is going into the plane of the board. So V cross B would be towards P. So P would be at a higher potential compared to Q. So this entire thing behaves like a cross PQ. It behaves like a battery of EMF. Epsilon PQ as shown with polarity as shown. Right? Where epsilon PQ is this. Now a resistance R is connected between points P and Q. There is a resistance R connected between P and Q. So then there is going to be a current that is going to be driven. The induced current will very clearly be epsilon PQ by the resistance R. Epsilon PQ by the resistance R. That's going to be the induced EMF. As simple as this, right? Let's look at problem number 2. Now, problem 2 is as follows. There is a battery of EMF 20 volts. There is a semicircular ring here. radius 5 meters, say PQ is, the length PQ is 10 meters. And this ring can slide along this vertical length, right? The mass of this ring is 1 kg. And can freely slide on two vertical supports. And this is given to be the diameter. That means the center of this ring will lie somewhere here. And the ends are connected to a 20-volt battery, and this is a region, this entire thing is a region of B equal to, going into the plane, equal to 0.5 Tesla. This ring has a resistance R. This ring has a resistance R, which is given to be 5 ohms. And the resistance of the poles which complete the circuit is negligible. That's given. We want to find the speed of the ring as a function of time. Okay. Now, let's look at this problem ab initio. Very simple stuff really. First of all, if the ring moves, there is going to be motional EMF across PQ. Electrically, the circular ring can be replaced by a straight wire PQ, right? So let's do that first level of simplification. This circular ring could be replaced by a straight wire PQ, right? Now, mechanically, the force acting at time t equal to 0, there is mg acting downwards, which is 10 newtons, right? And realize that at time t equal to 0, there is a current I that circulates in this loop. The current I that circulates in the loop at time t equal to 0, say I naught, is 20 divided by the resistance, which is 4 amps, right? Okay. So there is a current I naught equal to 4 amps that is being driven through this, right? So this is a current carrying wire placed in a magnetic field. It's going to experience a force, right? Now, the magnitude of the force is going to be BIL. The direction of the force is going to be given by DL cross B. DL is like this, the direction of current. B is like this. So DL cross B would be upwards. So it experiences a magnetic force FM upwards. It experiences a initial magnetic force FM, which is B 0.5 I naught, which is 4 into length L, which is 10. 20 newtons is the force that it experiences upwards. There is 10 newtons downwards. So it will begin to accelerate upwards. It will develop an upward velocity. Yes or no? Okay. This guarantees us that it will develop an upward velocity. Now, t seconds later. So that's the initial state. T seconds later. Now, one more thing, just to get a qualitative feel for things. While it develops a rightward velocity, while this develops an upward velocity, there is going to be motional EMF, right? V is upwards, B is like this, V cross B is like this. So, develop a motional EMF that will oppose EPSA. That means the current will decrease, the magnetic force will decrease. If the current decreases, the magnetic force will decrease while the velocity still increases. As long as the upward force is greater than mg, the velocity will go on increasing. But the force goes on decreasing. That means the acceleration goes on decreasing. Right? At some point of time, Fm will become equal to mg. And when that happens, acceleration becomes 0, the velocity of the connector becomes equal to what is referred to as terminal velocity. Velocity of the connector then becomes what is equal to the terminal velocity, right? So it's a state in which the upward force goes on decreasing, so the acceleration goes on decreasing. At some point of time, the upward force becomes equal to the weight, acceleration becomes 0, velocity becomes constant, that velocity is the terminal velocity. This is what is happening qualitatively, right? This is the steady state kinematic condition of the connector. This is the steady state kinematic condition of the connector when the velocity remains the same subsequently, right? Now, let me look at an intermediate state after a very long time. No. All the work done by this will get consumed in Joule heating of the connector. This is what will happen. There will still be current. I square R will come out of the battery. That will be in balance. Okay. Magnetic force will remain 10 newtons subsequently because current will not change. The magnetic force will not change. So, at some instant of time, let's say, velocity becomes v at an instant of time t. Right? There is going to be a motional EMF across PQ at this instant. Is BVL. Now, I'll tell you, even though I looked at the polarity of P positive by looking at V cross B, but I didn't have to do that. I'll tell you, the direction of the induced EMF, which is this, will oppose the fundamental cause, which is causing change in flux associated with it. See, essentially, there is change in flux caused in this because this is moving. Why is this moving? Because there is a current. Why is there a current? Because there is a battery. Yes or no? Right? So the cause is the battery. The devil is this battery, which is instrumental in causing the change of flux. So the direction of this induced EMF must oppose EPSA, and that will happen if it was disposed as shown. Yes or no? The area is increasing if it is moving the air, so the flux is increasing, isn't it? The flux is increasing. It's not the magnetic field, it's the flux. The flux is changing because of the motion. And that from Lenz's law must be opposed. The root cause of change of flux is this battery. Therefore, this induced EMF must necessarily oppose that change. Right? Now, in any case, this is the electrical state of the rod at an instant of time t, and it has a velocity v. Right? The current driven through the loop at this instant of time, the current driven through the loop at this instant of time would be EPSA minus BVL divided by the resistance R. Right? So the current at this instant of time is EPSA, which is 20, minus B, which is 0.5, into V into length L, which is 10, divided by the resistance R, which is 5. Yes or no? So that becomes 4 minus V amps. 4 minus V amps when the velocity of this has become V. Right? 4 minus V amps. Now, the mechanical aspect, there is a magnetic force that acts on it, which is BIL will be the magnetic force that acts on its upwards, right? DL cross B, so DL cross B would be upwards. DL is like this, B is like this, so DL cross B is upwards. The net downward force is going to be BIL minus mg, and that must be m dvdt. That must be m dvdt, yes or no? So net upward force. So now the mechanical aspect of the problem, the net upward force B into I I at this instant is 4 minus V. Bi into the length L, which is 10, minus mg. Mg is 10 newtons. Magnetic force minus gravity, that must be m, which is 1 into dv dt. That's the equation of motion of this connector. That's the equation of motion of this connector. Yes or no? Net upward force BIL, downward force mg is m dv dt, applying Newton's second law to the connector. This is what transpires. Yes or no? Which means now dv dt 10 minus 5v. Yes or no? 520 minus 10 minus 5v, which is 5 into 2 minus v. That's dv dt. Right? Very clearly, see, terminal velocity is a state where acceleration becomes 0. That means a state where the net force becomes 0. Right? So if someone wants to find the terminal velocity, then that will be physically a state where the net force is 0 or acceleration is 0. Acceleration 0 means this becomes 0. That means when v is 2, then that 2 meters per second will be the terminal velocity. Yes or no? That 2 meters per second will be the terminal velocity. Now, I need to find velocity as a function of time. So, for finding the terminal velocity, you can do two things. One, find the expression for the net force, equate that to 0, you will get v equal to v terminal. That's one thing. Or you can solve for v as a function of time, and then in that expression, as t tends to infinity, v tends to v terminal. As t tends to infinity, v tends to v terminal. That also, but we don't have, if you have to just find v terminal, you don't have to find v as a function of time. You could have just set the net force equal to 0 and solve for v. That's going to give you v terminal. You know what I'm saying? Right? So, dv by 2 minus v is 5 dt. Right? I integrate both sides. When t is 0, v is 0, it started from rest. When t is t, v becomes v, right? So on integrating, we end up getting minus log 2 minus v, or log 2 minus v, v runs from 0 to v, is minus 5t, right? Or log 2 minus v by 2 is minus 5t, or v is 2 into 1 minus e to power minus 5t. That's velocity as a function of time. Very clearly, as t tends to infinity, v tends to 2, which is the terminal velocity of the rod. Got me? Let's look at problem 3. There is a capacitor. There is a moving connector here. An initially unstretched spring of force constant K fixed at this end, halfway. The connector has mass m and length L, and this entire region is exposed to a magnetic field B going into the plane of the board. The spring is initially relaxed, that's given. And at time t equal to 0, the connector is suddenly imparted a velocity v naught to the right. Okay. We now want to be able to find the maximum compression brought about in the spring. We now want to be able to find the maximum compression brought about in the spring. Clear? See, first things first. This external impulse is given by an agent. What is the kinetic, what is the total energy given by the agent to this system? No. I'll tell you one thing which you'll see very shortly. If there was just an isolated, if it was just an isolated conductor imparted a velocity v naught, even though it could have been placed in a magnetic field, but there wasn't a complete circuit, then the energy given by the external agent would have been half mv naught squared. But now what really transpires is, see, no. Please listen to me. The moment this has to be given a velocity v naught, there is a motional EMF that develops across this. Now, there is a motional EMF of this kind. Epsilon that develops across this at time t equal to 0, say epsilon naught, right? That epsilon naught is b v naught L. I hope all of you understand this. And the polarity also, v is like this, b is like this, so v cross b would be like this, higher potential compared to this. Now, this entire EMF at that very instant must appear across the capacitor, right? So there would be charge accumulation on the plates of the capacitor, Q naught, Q naught. At this instant, time t equal to 0. What is Q naught? Q naught then would be C times epsilon naught, right? And there would be Q naught squared by 2C as energy, electrostatic energy between the plates of the capacitor at time t equal to 0. So at time t equal to 0, what's the total energy of the system? Q naught squared by 2C plus half m v naught squared. So the energy imparted to the system is half m v naught squared plus Q naught squared by 2C. If the energy imparted was only half m v naught squared to the system, then the velocity of this would have been less than v naught. You know what I'm saying? I'm saying if the external agent imparted energy equal to half m v naught squared, then the part of the energy will be available here, and therefore the velocity of this would be less than v naught. You know what I'm saying? Right? So then, in order that this could have a kinetic energy half mv naught squared, the total energy given must have been more than half mv naught squared. What's the total energy given to the system at time t equal to 0? Half m v naught squared plus q naught squared by 2c. Yes or no? Right? No, not complete circuit. I mean, there has to be, yes. If some energy appears somewhere else also, that also has to be provided by an external agent. Bolo? And do you realize that this V naught and Q naught go hand in glove? So while this moves to the right, the spring compresses and it retards the connector, the velocity of the connector decreases, so Q naught will also decrease. Q naught will also, if V naught decreases, epsilon naught decreases, so Q naught will decrease, right? So when V naught becomes 0, Q naught will become 0. At the instant of maximum compression, the velocity of this becomes 0, the electrostatic energy in this becomes 0. And the entire energy appears as elastic potential energy in the spring in a state of maximum compression. That means this entire quantum of energy appears as half k x max squared. where Q naught, like I said, is C epsilon naught, etc. And you can calculate the maximum compression in the spring. Got me? No. Yes. So there also, but the point is, let's say if there was an inductor element here, right? So at time t equal to 0, there is di dt, there is no current. Agreed, there is going to be di dt. There is going to be L di dt, but I is 0 at time t equal to 0. See, let me address this question and share it with all of you. Suppose this was an inductor element. Okay. And this was given a velocity v naught to the right. Then this epsilon naught will be L di dt. Right, where I is the instantaneous current. Now at time t equal to 0, the inductor will not build a non-zero current in it. The current will be 0. So half Li naught squared will be 0 in the inductor. You know what I'm saying? So then the energy would provided would only be half m v naught squared if this was an inductor element. I'll repeat, kya? Huh? Why is? Confused, kya? Tell me. Got me? No, suppose there was a resistance. Then yes. So it depends on the element, like I said. If there was a resistance, then instantly the current will build up to epsilon naught by R. And there would be power epsilon naught squared by R. Yes, yes, yes. Because where will that energy come from? It not only has kinetic energy, it's also accounted for the energy lost in the resistance. Isn't it? Okay, I'll repeat the last part. Suppose this was an inductor element. I'll redraw the circuit. Can I wipe this off and just redraw the circuit for you for an inductor? Hey, if an inductor element, pure inductor, let's say no resistance, if an inductor element is connected to a battery, so think of it very simple. Then at time t equal to 0, what is the current through the inductor? 0, right? 0, current is 0. Yes, yes, yes. It offers infinite resistance at time t equal to 0, 0 current, right? But there is a non-zero di dt. I is 0, but di dt is not 0. However, since I is 0, the energy in the magnetic field of the inductor element would be 0 half Li squared, right? So if this was, say, an inductor element, this was the connector, this was the connector, this was P, this was given a velocity v naught, so there is going to be b v naught L as the EMF, which appears across this, which would be L di dt, which would be L di dt, right? Now, what's the energy associated with the magnetic field lines of this inductor at this instant? 0, because at this instant, at time t equal to 0, this is not 0, di dt is not 0, but I is 0. Di dt is not 0, but I is 0. Isn't it? That's how current builds up in the inductor element. It has electrical inertia. At time t equal to 0, it has 0 current, but non-zero rate of change of current. See, current time characteristic in an inductor is this. This is the current time characteristic in an inductor. Yes or no? At time t equal to 0, I is 0, but di dt is not 0. Right? Yes or no? This is what happens. Therefore, at time t equal to 0, when this had to be given a velocity v naught, this was not consuming any energy. Right? This didn't have half Li naught squared was 0. So the only energy required that time was half m v naught squared. Got me? Now, Okay, let's, for the, half Li squared will be there. It will come at the expense of the kinetic energy of the rod. Right, and part of it is available as energy stored in the spring. So the energy equation would be half Li squared plus half mv squared. That appears as half kx max squared at the instant of maximum energy. T seconds later, velocity of the connector has become v. No, at the instant of maximum compression, yes, it will become 0. It will become 0. Yes, v will be 0 at that instant of time. See, there will be a resistance. Eventually, if there is a current, there will be a resistance also. Otherwise, it will reach an infinite value. There will also be a resistance in the inductor. So, theoretically, that will happen, isn't it? Let's look at problem 4. Right then, your attention please. So we have a situation of this kind. This apparatus resting horizontally, length L, and there is a see, this is resting horizontally and there is a vertical magnetic field B. There is a vertical magnetic field B, right? This L-shaped structure, U-shaped structure is resting horizontally and there is a magnetic field B upwards. There is a pulley and there is a mass M connected at this end, right? This is a massless rod. This is a massless rod and has resistance R. This is a massless rod. Let's say PQ is a massless rod and has a resistance R. There is no friction anywhere. The string passes over a pulley connected to a mass M hanging vertically. There is a magnetic field B existing perpendicular to the table. If the system is released from rest, calculate the terminal velocity achieved by the rod PQ and the acceleration of the mass at the instant when the velocity of the rod is half the terminal velocity. Okay. Now, very clearly this will develop velocity, right? This will develop velocity. T seconds later, say this develops a velocity v. The mass also would have had a velocity v, right? Now, v is like this, b is like this. So, what would be the direction of v cross b? Towards p or towards q? P, towards P, right. So P, if I look at PQ, epsilon across PQ is going to be BVL. That's the induced EMF, right? What's the current, induced current? Epsilon by R? BVL by R is the induced current, right? Epsilon is BVL. Epsilon by R is the induced current, I. Yes or no? Now, I can just close my eyes and say that the magnetic force would have to be leftwards. The cause of change of flux is the rightward velocity of this. The direction of the magnetic force must oppose that cause. So it has to be, without doing a dl cross b, I can claim that it has to be leftwards. See, the current driven is like this, right? So dl is like this, b is like this, dl cross b would have to be like this. But I didn't have to do that. I can be sure that it has to be leftwards only. Yes. So there is a magnetic force BIL leftwards. What is the magnetic force? BI. I is BVL by R. BIL. That's the magnetic force leftwards. So which is like B squared L squared by R into V. That's the magnetic force. Right? Easy to see that if T is the tension in the string at this instant of time, since the rod is massless, T minus Fm would be m dv dt. T minus Fm. Fm is B squared L squared by R into V. Right? That's a net force. Free body diagram of the connector. That must be mass of the connector, which is 0 into dv dt. So T becomes equal to the magnetic force B squared L squared V by R. V. Very clearly, as V is increasing, tension is increasing. Come to the point here. If you look at the free body diagram of M, mg remains same and T is increasing. So at some point of time, T will become equal to mg. When T becomes equal to mg, it will reach a state of terminal velocity. Yes or no? When T becomes equal to mg, it will reach a state of terminal velocity. V will be V terminal then. So if I have to write the free body equation of motion of the mass small m, mg minus T, which is B squared L squared by R into V. That must be mass into acceleration of the mass. And V will be V terminal when dv dt is 0. That means when this is equal to mg, right? So V terminal then V terminal is mgr. V will be V terminal when this is equal to mg, mgr by B squared L squared. That's V terminal. Right? That's V terminal. I want to find the acceleration of the mass when V is half of V terminal. Do you all understand this? Now, when V is V terminal, this is equal to mg. When V would be V terminal by 2, this will be equal to mg by 2. Yes or no? Forget this. When V is V terminal, this becomes equal to mg. When V is V terminal by 2, this will become mg by 2. Yes or no? So, when V is V terminal by 2, this quantity becomes equal to mg. So, the net force acting is going to be mg minus mg by 2 would be the net force acting. That will be the net force acting divided by mass m will give me the acceleration g by 2 of mass m when V is V terminal by 2. When V is V terminal by 2, the net force is going to be mg minus this will become mg by 2 divided by mass will give me the acceleration dv dt. So which is g by 2 when V is half of V terminal. Yes or no? Okay, when V is V terminal, this must become equal to mg. Because net force is 0, isn't it? So when V is Vt, this will become mg. But when V is Vt by 2, this quantity will become mg by 2. So the net force would be mg minus mg by 2, and that divided by mass will give me the acceleration g by 2. Is it confusing? No? So PR and QS are two conducting rails. And this is a conducting wire of mass M and length L. This is a conducting wire of mass M and length L. The ends P and Q are connected to a capacitance C, and a uniform magnetic field B exists into the plane of the board. This wire is pulled with a constant force F to the right. We want to find the acceleration of this, ignoring electrical resistance and friction. Ignoring electrical resistance and friction. What I'm saying? So, under the influence of this force, this will develop a velocity v. And there is going to be an induced EMF epsa like this, which is BVL is going to be an induced EMF, right? And this induced EMF will appear across the plates of the capacitor. So there is going to be charge accumulation on the plates of the capacitor. Q then would be C times epsa. Now, in order to find the acceleration of this, I would need to know the magnetic force on this. See, eventually there is going to be a current driven this way, which will result in a magnetic force BIL this way, right? So the net force is going to be F minus BIL. Now I need to know I. To know I, let me differentiate this with respect to time. So I then is going to be BLC into dV dt. This will give me I. dq dt is BLC into dV dt. That will give me I, right? So the leftward magnetic force is going to be BIL. The rightward force is F. So if I deploy Newton's second law to this connector, then the equation of motion of the connector is F minus magnetic force BIL, which is B squared L squared C dV dt. Yes or no? BIL, B squared L squared C dV dt. That must be equal to M dV dt for the connector. Right? dV dt is the acceleration of the connector. So very clearly dV A, which is the acceleration given by dV dt, is F divided by M plus B squared L squared C. So both these are moving connectors of, this is mass M1 and this is mass M2, and this entire region is a magnetic field B going into the plane of the board, and the two connectors are pulled with a force F each. This is F to the left, right? This is F to the left. The length of each connector is L. Both these connectors are of length L. And we want to find the current in the resistor as a function of time. Okay. Now, under the influence of these forces, both these connectors would develop velocities, right? At some instant of time, let's say this connector develops a velocity v1 to the right, and this connector develops a velocity v2 to the left, right? Then there is going to be motional EMF in both these connectors, right? In the connector of mass m1, this is the connector of mass m1, this connector, right? There is going to be epsilon 1, which is bv1l, yes or no, this way. V1 is like this, B is like this, V cross B is like this. So positive, negative, this for this connector. This is the electrical equivalent. For this connector, mass m2, this is moving with a velocity v2, mass m2. The electrical equivalent is epsilon 2 equal to bv2l, is bv2l, right? Do you then realize that this bv2l and bv1l are in the same sense in the electrical circuit? In the electrical circuit, this is the equivalent electrical circuit at an instant of time t, right? The current in the circuit at this instant of time t is going to be epsilon 1 plus epsilon 2 by r is going to be the current in the circuit at this instant of time. Clear? Right? So far so good, right? So that's the current driven in the loop. Very clearly, there is magnetic force acting on this connector, BIL leftwards. And the magnetic force acting on this is going to be BIL rightwards. Do you all realize so? Because currents are in opposite sense, DL cross B would be in opposite sense. Or even without that, you know, the motion of this leftwards would have to be opposed to dilute change of flux. The motion of this to the right would have to be opposed to dilute change of flux. So even from those considerations, these would be the direction of magnetic forces. So I can write the equation of motion for this. F minus BIL is M1 dV1 dt. For this, F minus BIL is dV2 dt. M2, right? Yes or no? Of course, this is BL V1 plus V2 by R. That's the current, right? Equation of motion of this connector is F minus BIL is M1 dV1 dt. That's the equation of motion of this connector. F minus BIL is M2 right? I need to find I as a function of time. I need to find I as a function of time. I need to eliminate V1 and V2 therefore. Right? What I do is I divide this equation by M1, I divide this equation by M2 and add these two equations. Right? So if I divide 1 and 2 by M1 and M2 respectively and add the two equations, this is what I get for the left hand side. On dividing by M1 and M2 both these equations and adding, this is what I get. And the right hand side is ddt of V1 plus V2. This is the right hand side, right? Now V1 plus V2 is what? Ri by BL. V1 plus V2 is Ri by BL. Right? And 1 by M1 plus 1 by M2 is 1 by mu, the reduced mass of the system, right? So this equation becomes F minus BIL by mu, where like mu is the reduced mass, M1 M2 by M1 plus M2. F minus BIL by mu is R by BL di dt. R by BL will come out of the derivative sign, di dt, right? And you can integrate this, di by this is dt by that, etc. At t equal to 0, I was 0. They started from rest, no velocities, no EMF, no current, and t equal to t, I is I, you can integrate. You'll get a logarithmic integration, and therefore I will become exponential in character. Yes or no? Right? Simple to integrate. Confused? Let's look at problem 7. So we have an infinitely long current carrying wire, carrying current I equal to 33.6 into 1 plus 2t milliamperes, that means into 10 to the power minus 3 amps. That's a time varying current flowing through this. Okay. And there is a circular loop whose center is at a distance d equal to 1 meter. And whose radius r is 10 to the power minus 3 meters. The resistance of this loop is given to be equal to 8.4 into 10 to the power minus 4 ohms. That's the resistance of this loop. We want to find the magnitude and direction of the induced EMF in this loop. Okay. Now, this current produces a magnetic field into the plane of the board. So there is a magnetic flux associated with this loop. Now when I varies, the magnetic field in this region will vary as a function of time. So there would be change of flux associated with the loop as a function of time. So there is going to be an induced EMF, and therefore there is going to be an induced current in the loop, right? Now realize that this distance is 1 meter, and the radius of this loop is 1,000th of a meter, right? That means compared to this distance, this is really small, and this could be imagined almost to be a region of uniform magnetic field, because this area is really small. The radius of this loop is really small compared to d, right? So the magnetic field at this point, at the center of the loop, is practically the magnetic field everywhere in this loop. So that's a good enough approximation. So the flux associated with the loop is going to be magnetic field at the center into area of the loop. That's going to be the magnetic flux associated with the loop at any given instant of time. Now what's the magnetic field at the center of the loop? Mu naught I divided by 2 pi d is the magnetic field at the center. That's practically the magnetic field everywhere in this loop, into pi r squared. That's the flux associated with the loop. Yes or no? So the induced EMF is going to be d phi dt, which is like mu naught r squared by 2d di dt. And di dt you can find from these considerations. That's going to be the induced EMF. The current, induced current, would be epsa by r. Epsa by r would be the induced current in the loop. Yes or no? Now, the direction. See, when I is increasing, B in this region is increasing. So the field lines going into the plane of the board, they are increasing. So the induced current must throw some flux lines out, some field lines out. So that will happen if the current was flowing in this sense. If the induced current was like this, then it will partially mitigate the enhanced flux lines going into the plane of the board. Yes or no? You know what I'm saying? Now tell me, if I had written epsilon is minus d phi dt, how would that give you the direction of the induced EMF? Will never. I told you at the very onset that minus sign is piece of CRAP. Right? It will not give you the direction. You will have to obtain the direction from independent considerations. Direction of the induced EMF. Got me? Okay. See, when I is increasing, there are more field lines going into the plane of the board. So then the direction of the induced current must be such that it must throw some field lines out. If the current was flowing this way, induced current, then it will produce a magnetic field all by itself in this region which comes out of the plane of the board. So that will decrease the flux lines going into the plane of the board, yes or no? So current could have either been like this or like this. If current would be like this, then it would be promoting more field lines going into the board. But if current is like this, then this current by itself will produce a magnetic field in this region which would be outwards. Right? Are you all okay with this? Is there any confusion? No? Okay, let me solve the problem. Prakhar is saying, what if the radius was not small compared to d? Let me solve the problem that way then. Okay. Okay, let's look at the problem. If r was not small compared to d. See, if this was a current carrying element, this was radius r and this distance was d. Was d. What I do is, this is the center, I break this into strips of this kind. Say this is a strip located at a distance x from this current carrying wire. The field at every point of the strip would be mu naught I by 2 pi x. Now, if dx is the thickness of the strip, then mu naught I by 2 pi x into area of the strip would be the flux associated with the strip. Now, realize that if this is x, this length would be d minus x. This length would be d minus x. This is the radius r. So this length would be what? This length, that means let's say this is PQM. The length PM from Pythagoras theorem is going to be what? Root r squared minus d minus x whole squared. That's PM. So PQ would be twice PM. That's PQ. Right? Now, so the field at every point of PQ is mu naught I by 2 pi x. The area of PQ is going to be the length PQ into dx. So the flux associated is this into dx into PQ. Twice root r squared minus d minus x whole squared into dx. That's the flux associated with this. The total flux associated with the circular loop would be x runs from this point d minus r. This point is d minus r, right? This is r. So this length is going to be d minus r. X runs from d minus r to d plus r. That's going to be the total flux. You will have, isn't it? Okay, I mean, that will be obtained if you took d minus x as r sin theta or r cos theta, you will get the same thing, which is fine. Right? You can integrate this and do the needful. Very complicated, and this would be accurate calculations. Differentiate this with respect to time, you would get induced EMF, very accurate. It will differ only in the, if r was small, it will differ only in the second or the third or the fourth place of decimal if you do this calculation, if for r is small. So then if r is small, then why bother about the third or the fourth place of decimal in the calculations? Be like an engineer, then not like a physicist. Settle for a practical solution to the problem rather than a theoretical and unpractical solution to the problem. I mean, it doesn't make sense if until and unless it's a space application or an application that requires a lot of accuracy, you don't want to waste time doing so much of computation for the fourth place of decimal, right? So in case it's not very small, if small r is not very small, then these are the computations that you need to do. As simple as that. Clear? So then we have an arrangement of the following kind. This entire region has magnetic field B. This entire region has magnetic field B. Say this is PQ, PQ is L, and the magnetic field is going, I'm not doing AB because B is magnetic field, so let me just call it PQ. This AB is a connector of mass M and length L, and it has resistance R, and it's fixed at P, it's hinged at P, it's hinged at P. The end B of the rod, that means end P of the rod, okay, end Q of the rod is always in contact with this conducting ring, is always in contact with this conducting ring. We want to find it, this starts from rest, and we want to be able to find the angular speed of the rod as a function of time and the heat generated in the rod as a function of time. These are the two things. This is the rod PQ, right? Okay. And it's not placed vertically. The whole thing is placed horizontally. Then gravity will not matter. Gravity will not be a force. This entire arrangement is placed horizontally. That means this axis will be vertical. This will be not a horizontal axis, this will be a vertical axis. So I hope you realize I don't have to look at gravity as an entity here. Huh? Now, see at time t equal to 0, what happens? In this complete circuit, the EMF is epsa. The current driven is going to be I naught, which is epsa by R. I naught would be the current which will flow through the circuit and is going to be epsa by R. Right? Now what would this current do? PQ, there is a current I naught. This is a current carrying conductor placed in a magnetic field. It will experience a magnetic force, right? This is DL, this is B. DL cross B would be like this. So every element from P to Q will experience a downward magnetic force, and since it's hinged at P, let's say the force acting on any element, will produce a torque about P in this sense. The torque about P in this sense will cause the rod to swivel about P and develop an angular velocity. There is going to be an angular acceleration and there would be an angular velocity that will develop in due course. At t equal to 0, omega is 0, right? But angular acceleration is not 0. Why? Because the force acting on PQ, you can imagine that force to be concentrated at the midpoint of PQ. Then force into half of PQ would be the torque about PQ, and that will produce an angular acceleration about P. Yes or no? Angular acceleration. So there is going to be tau equal to I alpha, producing an alpha, which will build an omega in due course, right? I want to be able to find omega as a function of time, the angular velocity in the rod as a function of time. This is what we need to take care of. Clear? So now, t seconds later, the rod would have swiveled to this position. T seconds later, the rod would have swiveled to this position. Instead of horizontal, it would have got inclined. And it would have developed an angular velocity omega. Then there is motional EMF in this rod at this instant. What is the motional EMF? Half b omega L squared is the motional EMF, right? So the motional EMF at this instant of time t is going to be, it's in a state of pure rotation about p. So half b omega L squared is going to be the motional EMF. Half b omega L squared is going to be the motional EMF. Now, the sense of this motional EMF. Let me tell you, first of all, I didn't need to do any calculations or any sign direction check to know what's the direction of this motional EMF. I can tell you that, well, the cause is the current I in this direction. Motional EMF must oppose this I. Motional EMF must oppose EPSA, because EPSA is the fundamental cause. The motional EMF must oppose EPSA. So even without doing any hanky-panky, I can tell you between P and Q, this would be the direction of motional EMF, let's say across PQ. This is EPSA PQ. This must be the sense of the motional EMF. It must be in opposition to EPSA. Must oppose I, so must oppose EPSA, right? If you want to get very finicky about things, then if you look at a small element here, that element has a velocity v this way. So if v is like this, b is like this, then v cross b would be towards q. If v is like this for this element, b is going into the plane of the board, then v cross b would be towards q. So q would be at a higher potential compared to p, which is what you see here. No? But didn't require to do that. I knew for sure that it must oppose EPSA, the fundamental cause for the change of flux. Now, in any case, the current driven at this instant would be what? EPSA minus EPSA PQ divided by R is going to be the current at this instant, right? The current at this instant that's going to be the current at this instant. Now, if you look at any element at a distance x on PQ, an element of length dx, this is an element of length dx on PQ, then it's a current carrying element. It's a current carrying element, and placed in a magnetic field, it will experience a magnetic force. This is dl is like this, B is like this, dl cross B would be like this. So it will experience a magnetic force df this way, which would be bi dx. Df would be bi dx. Yes or no? And this df will produce a torque about P. The torque about P is going to be df into x, right? So the torque about P produced is going to be df into x. df, which is bi dx. df is going to be bi dx. bil, L is the length, dx is the length. bi dx into x will be the torque about P. The total torque about P would be sum of all of this, where x runs from 0 to L. That's the net torque about P. Yeah. See, this is a current carrying wire. It's going to experience a force, and every force element will produce a torque about P. See, I'm accounting for omega. That's why I'm taking torques, right? So if this was a small element between P and Q at a distance x from P and of length dx, dl is like this, B is like this, so dl cross B would be in this sense. And what would be the magnitude of the force? Bi dl, so Bi dx is the force. This force produces a torque, force into x. Torque in this sense, clockwise sense, yes or no? The total torque about P is going to be sum of all of this, where x runs from 0 to L. That's the net torque about P. So the net torque about P is going to be this integral, which is Bi L squared by 2. That's the net torque about P. Which is what I told you initially. BIL into L by 2. I wanted to justify that, so I did this calculation. What is realize I told you when I started, I said there is a force acting on it which could be imagined to be at the midpoint of PQ, and then BIL into L by 2 would have been the torque, right? But since I wanted to justify this, that the same, I carried this calculation out, right? So that's a net torque about P, and that must be equal to I about P, moment of inertia about P into alpha. Yes or no? D omega dt, right? Isn't it? So what is I about P? 1/3 ml squared. So the net torque about P BL squared by 2 into I is given by this. I is given by this, which is epsa minus half B omega L squared by R is I about P, which is 1/3 ml squared into alpha, which is d omega dt. Tau is, this is the cause, this is the effect. D omega dt is the effect of this torque. And now you can easily integrate. You can write d omega by this is dt by etc. Integrate logarithmic, exponential is what you'll get. You'll get omega varying exponentially with time, right?
So why is the I is minus half of B omega?
Two reasons. First reason is no reason. It's just that it has the induced EMF half B omega L squared has to oppose epsa. I told you. Without even looking at directions etc., I can tell you that half B omega L squared, the induced EMF, has to oppose epsa, which is the fundamental cause of this motional EMF. The second thing I told you was, when I looked at PQ, current was being driven this way, right? Right? V cross B. This element here had a velocity v like this. B was going into the plane of the board, so V cross B was towards Q. So Q was at a higher potential compared to P. Therefore, the PQ was electrically represented like this. That was epsa PQ, half B omega L square. Yes or no? So if it was like this, it is obviously in opposition to this epsa. Do you see that? This epsa would want to drive a current this way, whereas this epsa PQ would want to drive a current the opposite way. So epsa minus epsa PQ by R. Are you lost or are you fine? Got it? So you can find omega as a function of time. You will get an exponential variation. And once you find omega as a function of time, then current, you can plug in that omega here and you would know I as a function of time. Once you know I as a function of time, power dissipated as a function of time would be I squared R. That would be known as a function of time. Got me? Shall we proceed?